All right, so we are in AP Calculus, lesson 11-3. Today's date is Thursday, March 12th, 3/12, 2020. So volume of sphere, or volumes of square cross sections. That's how you read that statement. And our objective today is, it's pretty straightforward, yeah. Go for it, someone.
Find the volume of a shape with square cross sections.
Yes, and you still read it better than I did. So as I was saying, there's technically, I could teach two lessons, like 11.3.2, 3.3 on square cross-sections would be the first one, then semicircle cross-sections, right triangle cross-sections. We'll see a graphic of how those change it. They're not that hard to discover on your own if you see them pop up. I'm definitely going to teach you this one because it pops up more often than the others, according to John. So if I have this shape, it's called a rectangular prism, I can find its volume. It's pretty straightforward. You guys remember how to find volume of a prism like this?
It's base times height times width.
Yeah, base times height times width, or length times width times height. I don't know, whatever you want to say. So length, I'm going to call that width, and I'm going to call that height. You just multiply them together. Doom! I don't know what that sound was. Done! You have your area. Pretty straightforward, right? So you can say volume, capital V is equal to length times height times width, or some version of that, maybe length times width times height. I don't know. That's probably the more typical one you find in a textbook. When do you learn this? I don't know, 7th grade-ish, I'm guessing? Yeah, somewhere around there. And then you can use it to estimate how many pennies you have in a certain area or a certain volume. So the cool thing about calculus is we kind of use this and advance it. So this area down here we can find, and that area is just length times width. So this length times width, that's the area down here, and we call that area base, capital B for base. And if you didn't know, base is equal to length times width, which means volume is now capital B times H. Wow, you've taught us so much, Mr. Sindel. You've combined one variable or two variables into one. Yes, but there is a reason for why I'm doing this, because I can apply it now to any prism or any prismatic shape or shape that has a right angle that comes up from here, which is going to be all the shapes in AP Calculus. So for example, if I look at a cylinder, so it's very similar. I have a base shape that I'm talking about. So I'm going to call this base shape capital B again. So if I'm trying to find the volume is equal to, well, first of all, do you guys remember the volume of a cylinder?
Something half, right?
There's no half in this one.
I don't remember it, but for some reason I remember that I really liked the formula. I liked
Okay.
doing it.
Arrow, do you remember?
What was the question?
What is the volume of a cylinder?
Well, you have to find the area of the circly bits first.
What is the area of a circly bit?
Is it pi r squared?
Okay, and then?
And then the height.
There it is. Yeah, stego and arrow, you have it, times height. So that's the volume of a cylinder, but you can rewrite that another way, because again, this pi r squared is again just your base area, and I can say, yes, that's just base times height. And I love doing this in mathematics. I have simplified really hard things down into one simple formula. Just always do your base area, multiply by your height, you're done. That's exactly what we're doing today, but with calculus, and therefore it's going to be harder. I had to make it simple before I make it harder, because if it's already hard and then I make it harder, it's way, way too hard, right? And then if we didn't know, that's the radius. I should label it up there. And then the height is the height of the cylinder, and the base area is down here, and the base area is right there. Okay, so I've added all the notes I need. Let's talk about an even harder shape. Are you guys ready?
Yes.
I want everyone to draw a cool shape that has a line that it starts, and I don't know, some line that ends, and do some cool squiggly shape that you want. I don't care what it is, as long as it doesn't loop like that, as long as it's not needing to be represented by a parametric or polar equation, some actual function.
Oh, it has to be.
Yes, so make it continuous, in other words, or you're trying to make something discontinuous,
I
Aaron?
was trying to make something that didn't pass the vertical line test.
Oh yeah, it needs to pass the vertical line test, it needs to be an actual function. Draw something cool. And we're gonna say, hey, I can find the volume of this shape if I were to copy that shape and like stretch it out. So let's see how well you guys are at, and Mr. Snell also, at drawing 3D objects. So the way that I make 3D objects is I kind of extend lines. Let me, if I just extend one, ooh, here, I can use technology and make it even better than yours. See if you guys can beat Mr. Sindel. So I'm gonna do this line and I can copy paste it. It'll be the same angle. I can copy paste it there, copy paste it there. And then I can kind of just do my best attempt at... Ooh, did I draw a function? Oh, I can just copy and paste that function. Oh man, you guys are going to have to live up to Mr. Sindell's ability to do technology here. Why is this line not matching up though? These lines should match up. Why is it not? Oh, because that line is bigger. Okay, I guess I'll have to just draw that. Darn, I thought I could use technology as a replacement to my poor artistic skills. I can find the volume of that shape. Because, again, I can call this general shape that's really hard to find the area of, I can call that B. And as long as I'm given a function for that top one and the bottom one, the area of B is just the integral of top minus bottom. We saw that yesterday. Well, technically we saw it 2 days ago. 3 days ago, if you can include ski PE and the fact that we made an error in the last notes. Anyway, we've learned this before, and the height would be that height right there. What is the distance of that line? And now that I'm thinking about it, this height really should have been the same on both sides, so that's a tiny teacher mistake. That should have also been H. If you label them both H, you can just have an asterisk and say not drawn to scale. So that's what I'm doing right now.
Really, isn't that part of the base though, and the height is the orange one?
Height should be rough. Oh, I guess it doesn't really matter because for this one, our heights can be different depending on the types of functions. So you're right. Let's just ignore that for now. One of them is H,
Not
sure.
really what I meant, but okay.
Oh, what was your question?
See how there's orange lines and blue lines?
Yes.
Are the blue lines the length and width, and the orange lines the height?
So I'm calling, I guess the orange line should be the height. Yeah, you're right. Because otherwise that's just the, I don't know what that would be. It's the top minus the bottom function. So maybe I should make that H orange also to make that clear. Yeah, sorry about that.
Yeah, okay, slightly clearer now. So.
It should match up with the definition of these. I have the base area and then I extend that area. All right, so do your best attempt to, again, copy down these lines again over on your graph. Oh, weird. It grabbed everything. Okay, I can grab... Oh, so I can probably go like this. So if you have those exact same functions on a graph, and this is kind of converting the topic, or I don't know. Anyway, we're converting this into a graph that you'll see more typically on AP Calculus. They'll say if I have some f of x up here, f of x, and I have some g of x down here, I can make this line red as well to match that with the color. Then I can find what the area is in between them. Can you guys give me the formula for that again?
Based on height.
Not quite. So this is kind of review from lesson 11-2. Our formula was integral from a to b of
F of X.
Yeah.
f of x
dx.
minus g of x. Or more simply, it's top minus bottom. Okay, so this is kind of where we have to visualize things, and it's hard. So let's say I gave you these two curves. I think one is probably a sine wave and one is a cosine wave or something weird happening. But anyway, I give you two curves. And I'm going to say every single one of the distance and the heights is going to be represented by a square cross-section. What does that mean?
It means that the height and the thing are equal, right? That's
The-
part of it.
Yes, the height and then the area distance, I guess, is equal. So go ahead and just draw one line. And I'm going to definitely use technology because my lines need to be straight here. Go ahead and just draw one random line. Technically, there are an infinite number of lines here. We're just going to draw one of those infinite, so 0% of the lines, right? So if I draw one height right there, I need to make sure that when this pops out into the third dimension now, so you have to now picture maybe stacking a little square cookie or something, it is now going to pop out and it's going to have the same exact height as this line right there. So I don't know how to draw the third dimension very well, but I'm going to go like this. The same exact height is going to pop out of this page now. This is coming out of the computer, out of the screen, out of your paper when you're taking the notes. And then I have a square that looks like that. So I'm going to label it because maybe it's unclear, but this is a square. I'll say this is a square. And technically, that square actually does have thickness. I know that we have an infinitely thin slice here because I'm only talking about this infinitely thin piece right here, but really we started with a rectangle. If we started with a rectangle, that means we really have a piece that looks like this. I'm just going to add on to our shape a little bit. I'm going to grab a piece like that and paste it a few times. We really have this.
Looks like it's paper on its side.
Yeah, it does. Cool. So now we have a three-dimensional representation of what's happening. I have some piece that looks like that that's coming out. And really you need to be thinking of this as a very, very, very infinitely thin slice that I'm talking about.
Is this slice d of x?
The thickness is at d of x? Yes, the thickness is d of x. And I'm going to come label that. I just want to make sure that everyone has this down first. Gio looks like he's still working on it.
I don't know that.
Oh, are you decorating it with a logo too?
Mm.
So this thickness right here is d of x. So I'll just do an arrow. This thickness is d of x, which is going to get infinitely thinner. What is this height right here? Does anyone know this height?
H.
Well, let's assume that our red function is f of x.
It's the height of f of x minus 7.
And we'll call this blue one g of x. Yeah, so this height, as Arrow said, is f of x minus g of x. Minus g of x. So that represents this piece right there. That line segment is f of x minus g of x, but because it's a square, either stego or geo, how long must this piece be?
They're the same.
The same.
They're the same.
They're exactly the same, yeah. So I can say that that length right there, and I'll label it maybe down here, f of x, again, minus g of x. Minus, and I need some more room, move you over, f of x minus g of x. For that length. So we actually have all three dimensions. Just like we were doing before where we had length times width times height, we have the three dimensions of this rectangular prism. It's actually a square prism. Well, it is also a rectangular prism because a square is also a rectangle, but whatever. I want to show you what this actually looks like to help you visualize this. So I have a link here that I can click on. So clicky, clicky, and I get this. And you can see that this has the ability to do a bunch of different types of cross sections. So I'm going to click on, let it load, I guess. I'm going to click on square. Go away. And then this is when the internet goes down and then the entire lesson fails, right? There it goes. Okay, so if I click on square, you can say, oh yeah, there's your square cross section. This square has infinitely thin thickness. So everyone can see that kind of matches up with what we saw before, right? So let's go ahead and, I guess it doesn't matter where that square is, but notice that if it's up at the tip, it's a very small square, and I'd have to zoom in because that thickness is thinner, therefore the height has to be smaller as well. If it's right in the middle, then it's a bigger square. If it's right at the end, it's a very tiny square. It gets tinier and tinier. So we can visualize what each of the infinitely thin squares would look like. But what does the volume look like? So if I have n and I increase the number of segments, so obviously if I have a small number of segments, you can kind of visualize what it's going to look like. But what if I make n a really, really big shape? Or like n really high? There it is. This is the shape that I'm really talking about. I guess, what is the volume of that shape? If I were to put it in a blender, how much would it measure? And you have the ability to do that now. And you don't have to do squares either. So let me come back here and make n really small. I don't have to do squares. This lesson is all about squares, but I could have done equilateral triangles, and it does change the type of shape that you have. Equilateral triangles make a shape that looks like that. Semicircles, let's go back to n so you can see the semicircle. Semicircles look like that instead of the square, and then again, if I increase n, it looks like that. All right.
Susan, what would you use this for, like, practically?
Practically, it's a building block in how to find volumes of other shapes.
Oh, okay.
So it doesn't make sense to compare, like, I was thinking of like a pot to put a plant, like how much dirt do I need for this pot versus this pot? You can have any type of shape that you want, and you could evaluate what that is.
It's just another way to find areas, so.
It's a,
Even though nothing is shaped like that, but.
it's another way to find volume of things. So it's really important, like say you have some sort of NASA rocket and it has a weird shape, you're like, how much fuel can go in there? It's really important to know exactly how much fuel can go in there, so you need calculus to figure that out. But this is a simplistic view because every single one is a semicircle. With calculus, you can use different types of shapes, though. All right. So there's our square cross section. And I realized we did this backwards. We should have done this shape down here. But we can do is just draw the simple formula down here. Let's just draw, I don't know, any random shape. Go ahead and do shape. You can do the same exact one if you want. You can do some, it has to pass a vertical line test, so maybe a shape that looks like that. Go ahead and practice drawing a square cross-section and make it super simple. You don't have to make it 3D or anything. What would a square cross-section look like on your sample graph? So I'm going to make my sample graph kind of cool. There's my sample graph. What does the square cross-section look like? And it needs to be a sketch, so practice sketching. The first step to making your sketch is you need to draw the height. Once you draw the height, make the height pop out into the third dimension and make it have the same angle. And there's the square cross-section. And notice that if I did the square cross-section over here, it would be a lot tinier of a square. Everyone can practice drawing the square cross-section. It really does help if you forget what's going on. All right, so before we move on, the last thing that I want to talk about is the difference between perpendicular to the x-axis and perpendicular to the y-axis. So this graph that I'm giving you, let's all write it down also. This is perpendicular to the x-axis. Perpendicular to the x-axis. What do I mean by that? What I mean by that is when I'm drawing my first height, like this height right here in my graph, when I draw this first height, that height was perpendicular to the x-axis, and you know that the x-axis is that one. So the heights that I'm first drawing have to be perpendicular to the x-axis. I could have asked it differently. I could have said, draw this with it perpendicular to the y-axis. Instead of drawing a cube or a rectangular square, a square prism, there's the right word. Instead of drawing a square prism like that, I could have drawn a square prism that went like this. That was the height in terms of the perpendicular to the y-axis, and it pops out in this direction. So your heights, in this case, were perpendicular to the x-axis, which means something very specific. It means, and I'll put this in parentheses, I'll do it underneath because I need some room. We will have dx instead of dy. If it was the alternative, if it was perpendicular to the y-axis, so I'll just abbreviate here, perpendicular is P-E-R, perp to y-axis, we would have a dy when we're doing our integral. So if you ever see an integral with dy, then you know by default you're actually doing perpendicular to the y-axis. Or if it tells you, hey, make this perpendicular to the x-axis, you know you're going to have a dx. And you should be comfortable going both ways. I'm mainly going to be focusing on the easiest, like what is just perpendicular to the x-axis. We'll kind of do the same thing over and over again. All right. We haven't made a formula yet, so the last step is what is the formula whenever we are given a square cross-section. It's something that you should now be able to derive. It's essentially coming from this picture. All I'm doing is I'm multiplying everything together. So let's go ahead and relabel this picture on the back. So there is that slice that we just saw, and I'm going to call this front side facing us B. All right, what was the thickness of B? This thickness right here. This, is dx. And if it was perpendicular to the y-axis, it would have been dy. What about this? I'm going to call it the length here. What was the length up above? Say it louder. minus g of x, yes. And what about the side, or the height? Height is the same thing, so we can label it f of x minus g of x. And I should really be labeling the dx in like another color, like yellow or something. Okay, so let's plug it all together. I have to do the top minus the bottom times the top minus the bottom times d of x. I'm just multiplying those all together. And I have to throw that in an integral. By the way, this is represented with the cross section. So this category, I'm going to say this is the cross section that we are analyzing. And then we're going to convert that into an integral. All right, so the integral is going to be between, okay, we didn't say anything up here, but I'm assuming that it goes from 0 to 1 in this case, or a to b. So our general integral is going to be from a to b. In our case, it was from 0 to 1. Of what? We just need to multiply all these together, right? So I have an f of x minus g of x. Then I multiply that f of x times, or minus g of x, all that times d of x. So I'm going to put some parentheses around this. Oops. Oh no. I don't like how this program undoes things. So I have that term times our d of x term. So that's the formula. You just multiply them all together and then you take the integral, because the integral is used to find the area of f of x minus g of x. Okay, well we can simplify that in one more step, because if I have 2 f of x minus g of x's, I really have squared, right? So this is now really the integral, and this is the formula that you're going to star, circle, write smiley faces around. This is integral from a to b of that f of x minus g of x quantity squared, and then d of x. So that quantity squared d of x. And again, I'll say it again. This f of x minus g of x squared, that represents capital B. B again is just this length times this length. That is capital B. And then the height here is d of x. Height eventually goes to 0. So this is capital B that we were talking about. And then d of x, that was our height. So again, it all boils down into just capital base times lowercase height. You guys ready to try this out on some homework?
Where did the integral come from if it's based on side?
So in order to find the area between two curves, the general idea is you have to take the integral of the top minus the bottom. So if I want to find this area right here, I do the integral, because I'm counting up the infinite number of squares. So the integral in this case, since it's volumes, the integral in this case, because it's volume, I'm counting up an infinite number of these rectangles. We only had one rectangle right here. We have an infinite number of those, and in order to count infinity, we have to use an integral.
Yeah, okay.
Yeah, thank you for asking, because I should have made that clear. Other questions? All right, can you guys give me a fist of 5? How well do you think that you can find the volume of shapes with square cross sections? 3, 4, Gio, do you got? 0. All right, thank you guys.